So I think this chapter on organic chemistry might be the first time some of you have seen organic chemistry, although you deal with it all the time. So organic chemistry is really rather fun when you start with it, even though this is really just an overview of the topic. So you're going to get a lot of names and a lot of terms, but I hope when you look at it, you'll recognize some of this and understand the significance of it. All right. Now, I started off, let me just get this here. Yeah. So I started off, and here you can also, if you look at the molecules on the image here, it shows these specifically because they are organic. So what does that mean? And really, what does that mean? It means it's chemistry based on carbon. And historically, and I always try to put some sort of historical context into the chemistry in this course, I want you to understand where this came from, because even though organic molecules clearly are molecules of life, all right, because we are carbon-based, but that actually posed a problem to its study, because it was thought for a very long time that the only way to get organic molecules was from living things, all right? You can imagine why that was, all right? So when I tell you here that this scientist Friedrich Wörler was proved that you could get organic molecules starting from inorganic materials, this was a big deal. A lot of people did not want to believe this, right? Because the idea is that life can only come from life. And it really was this experiment that showed that this was possible. And this Miller-Urey experiment, we don't really talk about it in this course. You talk about it hopefully more in a Gen Bio class, but I spent some time going over the significance of this and the fact that you can actually get the molecules of life, which we'll be talking about shortly when we start polymers, starting with completely non-living materials. And so this is the significance here was huge when this happened, all right? But if we go down to the nuts and bolts of it, before we have fun with all these molecules, it's important to understand the historical context. And this was the birth of a new form of chemistry, which is organic chemistry, which is a full year of study if you're getting a chemistry degree and more. I studied this topic for a full year as a biochemist, but I could have studied more if I became an organic chemist. There was more courses to take. Of course, I come from a non-liberal arts background, so it's a little different, but just so you know that there's a whole version of chemistry that's just based on these molecules, all right? And hopefully looking at this chapter, you'll understand why and how important they are. But at its very basics, what is it? Well, it's the chemistry of hydrocarbons and the derivatives, and I'm going to sort of go back into what that means, all right? And now, at this point, there are tens of millions of compounds, and 95% of them are based on carbon, which is what we need for, Earth-wise organic chemistry, because I always hate using the term all, but almost all life on Earth is based on carbon, all right? And why carbon? Now, this goes back to our looking at the periodic table, and if you look at it in its column there's only 4 valence electrons, which makes carbon really promiscuous. And I already spoke about that in this course, all right? So it can form umpteen beautiful molecules, all right? Other types of molecules that could be possible would be, the next one would be silica. And if you're a Star Trek or a science fiction fan, you would remember, this would be the old Star Trek. There was an episode where, the Enterprise ended up interacting with a life form that was based on silica. And many of the Star Trek franchises have based, and I know for certain this happened again in the Next Generation. Here I am going all nerd on you, but it happened in Next Generation. There was also an episode based on looking at silica-based life forms as well. All right. And I'll let you, if you're a Star Trek fan, see if you can figure out which episode that is, but I'll give you a hint. It was probably in the first season. All right. So why? All right. So here's the 4 valence electrons, and that makes it very promiscuous. Not only can it bond with hydrogen, right, because we're talking about hydrocarbons, but many other different types of molecules, as well as itself, which is really important because since it can bond with itself, you can have single, double, and triple bonds, as you can see here. Then, of course, you can also bond with oxygen, nitrogen, hydrogen, sulfur, and you'll see halogens, and you can get all kinds of other weird structures, as you'll see as we go through this, okay? Now, and these can vary in length, yes, from 1 carbon to hundreds, thousands of them, if you're talking about a protein, and the double bonds can be in different places, and understand that positioning of these double bonds can give butene, in this case, 1 butene versus 2 butene, very different properties. And they can be branched, they can be linear, they can form rings, they can form double bonded rings, and they can be teensy tiny, or they can be huge. This would be a nanotube, not formed in a living molecule, but definitely being used in science and to perform all kinds of interesting things, from electronics to treating diseases. All right, so amazingly, carbon can do all of these things. All right, now getting into the nuts and bolts, right? So I said hydrocarbons. Well, they're the simplest types of organic molecules because they're just based on hydrogen and carbon. All right. When we look at this, there's different types of flavors of them, right? So we have ones that are called aliphatic, meaning that they don't have benzene rings, and aromatics, which do contain benzene rings, okay? What is a benzene ring? Well, that is a 6-carbon ring that has alternating single and double bonds, which makes it an amazing structure, which we're going to talk about in a short few minutes, okay? Now, so aromatic hydrocarbons have these benzene ring structures, or they can have properties that make them very similar to benzene, all right? And if you look at my notes on page 2, when I talk about aromatics and benzene rings, you'll see that I actually drew those double bonds as a short form with a ring in the middle. And the reason that is because those double bonds flip, all right? So those bonds spin, which give aromatics or benzene rings really interesting properties, okay? So as an organic chemist, you would draw that as a diamond with a ring in the middle, okay? So let's go through the different types of nomenclature, all right? Now, I hope you at least learn alkanes, all right, in terms of naming them. Because really what they are hydrocarbons that contain only single bonds, all right? And they're called saturated. And the reason they're called saturated is because they have no double bonds. So when you're talking about a saturated hydrocarbon, you know that there are no double bonds. And they're named by their number of carbons, up to 10, all right? After that, we don't worry about that so much. We give them different names. But hopefully you can at least learn them up to 10 because you probably already know these prefixes, right? So basically it's a prefix saying the number of carbons and then the word ene after it. And you can recognize an alkane because of this idea here, C to the N with H2N plus 2. All right, so basically you're going to have double plus 2 the number of hydrogens for those carbons, and that's because you remember carbon can form 3 bonds, so those carbons on the end need to bond with 3 carbons, and the ones in the middle are all bonding with 2. All right, so the plus 2 comes from the 2 extra hydrogens on the ends, and then this 2N meaning that you can form 2 hydrogen bonds with every carbon in between. All right, so in terms of these stems, they call them the stems. As I just said, prefixes, but they call them stems in your book. You probably already know everything from 5 to 10, right? Because it's logical, right? If you learn geometry. So pent always means 5, hex always means 6, hept 7, oct, of course, 8, non is 9, and dec would be 10, all right? As in a decade, right? Now up here, and hopefully you can just learn these other 4, right? So meth is 1, eth is 2, prop is 3 and bute is 4. All right, and I really would like you to learn those because you'll see these compounds in all kinds of stuff, and at least it will give you an idea of what they are. Okay. Now, understand, and if we go back here, right, I just showed you this picture of butene versus 1-butene versus 2-butene, or butane and methylpropane. Notice you've got branches, right? So these guys can, even though they might be have the same chemical formula, so these two are both based on 4 carbons, and then of course there's a double bond here which complexes things a little bit. The different positioning, so you can imagine you could have 4 here and then maybe have a branch here and then 2 here. Because of that, the different arrangements that those carbons can take, they're called isomers, all right? So here's butane and isobutane, all right? So here you can see that you've got 4 carbons in a line, right? This is the simplest way to do an alkane. But notice here, you've got 3 carbons with one of them sticking out, but still it's C4, so 4 carbons and 10 hydrogens, all right? So there's different ways of indicating the different types of butanes, and as you can see here, isobutane would imply that you've got 3 carbons with a branch on there, all right? And since you're only dealing with 4 carbons, the branch can only be in one place, so they don't really worry about telling you which place, but you'll see in some of the other molecules, you'll see they actually put a number in front to say where is that branch. So here it would be, well, I won't give you there's another way of naming this that would tell you where the branch is, other than saying isobutane, all right? But that's getting a little bit further than you need to know, all right? So just appreciate the fact that you can position those carbons in different places and you get isomers. So the structural formula of them would be a little different, even though the chemical formula is the same, all right? Now, there's 2 ways of showing these, right? You can have them condensed, showing you basically what they look like, which is very helpful for someone who's learning, right? But they'll take the bonds out to simplify it, so you can sort of understand that between each carbon and hydrogen there would be a bond. But this sort of lets you know that decane is a chain of 10 carbons with hydrogens bonded to that, and it's just implied that the carbons are bonded to each other. All right, so that would be the condensed structural formula, whereas the molecular formula will just be C10H22. All right, so there's different ways of listing them, and this is usually the way it's done, but this is really helpful when you're learning to do that, draw it out. If you're doing questions and you need to draw it out, go ahead. And it's very helpful to do that, okay? Now, notice that as you get more and more carbons, the properties will start to change, right? So you can see methane, right? You can see it as not that you're going to need to memorize these, but understand that, you know, the different length of these molecules is going to change the properties of the actual molecule, all right? First of all, one thing to know, and we'll talk about this later, these things are really nonpolar, so they don't like really to dissolve in water very well. The smaller the better, but once you get up to this guy, C20, this guy really doesn't really like to dissolve in water, and if you've ever worked with paraffin, you know that that's a really great way, if you make candles, they don't mix with water. Whereas some of the smaller ones, they might, so you've got some fuels, gasoline and that kind of thing, a little bit miscible with water. So that kind of thing is also to keep in mind, but notice that the boiling point really goes up the longer your alkane, as the melting point and the boiling point, I should say, both of them. Whereas here methane is a gas, right? So it can vaporize very, very low temperatures, and you can see that right here, okay? Okay, so very, very low melting and boiling points. I should say vaporize, very low. This is melting, this is boiling. And you can also see that the density, right? So these really small ones are gases. And then as you go up, and here, this one is a solid. So you can see that this, you know, the length really does have a difference on the physical properties of those alkenes, okay? different ways of drawing them. You might have seen people with chemistry sets. If you did this in high school, I have a chemistry set. My daughter was very excited to find out. I think it's in my office. I'm at home right now. She was wanting me to pull it out. Not because she's a chemist, but she used to play with it when she was young. So she just asked me about it the other day. But if you're doing with these, very often these are very helpful to appreciate the nuances of the structures. The structures, of course, give these very different properties, as we were talking about. But there's different ways of doing this. So ball and stick, and this would be space filling, right? So this would also give you an appreciation of the electrons around that carbon. So both of them are very informative in different ways, okay? Now, cyclic hydrocarbons, all right, so they're gonna lose hydrogen, right? Gonna lose 2 hydrogens, but you're gonna form bonds. The simplest cyclic hydrocarbon would be with 3, all right? So cyclopropane, and these ones are named with a cyclo in front. And notice you've got an ane here, so there's no double bonds. That's what this means. We're going to get into that in a sec. So here you got CnH2n, so you notice that you've lost your 2 hydrogens, so that instead they're now formed bonds with the other carbon. All right, and these can get bigger, so you can have cyclopropane, cyclobutane, as you go up, cyclopentane, etc. Okay. So here you go, cyclopropane, cyclohexane, cyclohexene. Now this brings me to the next thing, ene. And you probably noticed this back here when I showed you that structure with those double bonds. Notice we had an ene instead of an ane. All right, an ene implies that there is a double bond, and this 2 here tells you where and what position. So here, this is by the first carbon. You always start numbering closest to the double bond. And here, this would be at the second carbon, all right? Just so that you can appreciate what these mean. But for you guys, what do you need to know? Well, if you see ene, that means that you have a double bond. So you have cyclohexene, all right? So what does that mean? Well, we call these enes, alkenes, unsaturated, meaning that there are double bonds, okay? And they're named very similarly to the alkanes, only instead of ane, you say ene. So you have an ethane with a double bond, you have an ethene. And because we're dealing with carbon, of course, we can also have triple bonds, in which case now you're going to have 2n minus 2, all right? And how do you imply that? Well, you say ine, okay? So ethyne would be 2 carbons with triple bond in between, and these are the simplest that you'll get, all right? So ethyne has a common name called acetylene, all right? And you've probably seen that before in terms of a gas that is used for certain purposes, especially if you are an auto or you like to use gases in chemistry. But its common name is acetylene, but its proper name, and there's a history to this, is ethyne, okay? Now, where do you also encounter them? Well, you've probably seen them in diet, right? So saturated fats versus unsaturated fats. You've probably seen this on lists and ingredients, and we'll talk more about these later. But when you're talking about a saturated fat, okay, notice that this isn't just a hydrocarbon. There's something else going on here, which we'll talk about later. You can see there's a group on here, functional group. But what you're dealing with here are the hydrocarbon end here is fully saturated. So, and that would be like butter, right? They're solids. Whereas it's unsaturated, which is what you would find in oils, all right? There must be at least 1 double bond in this, okay? Now, the more unsaturated that hydrocarbon, the more liquidy or more fluid that that structure will have, all right? Now, the interesting thing is that these double bonds, and this is where we get into this idea of geometric isomers. Now, if you look at organic a little bit more and learn more about these molecules, you learn that single bonds, that the molecule can rotate pretty freely around a single bond. But once you introduce a double bond, there is a fixation there. It's fixed, and these atoms cannot rotate, right? So this is considered, very often it's called planar, so plane, meaning that those molecules are going to always have a very flat sort of surface, and that gets even more profound when you're dealing with a triple bond. Now, because of that, you can have isomers, all right? So if you have a double bond and both of the groups attached to either side of that double bond are on the same side, they're called cis. And if they're on opposite sides, they're called trans, all right? Now, why am I mentioning this? Well, because you do interact with these as a human being, and they're called trans fats, okay? Now, I'm going to sort of build up to this, all right? How do we get a trans fat? So basically what can be done is if you have a carbon structure that has a double bond, so you have an ene or an ine, particularly when you have an ene, you can do a chemical reaction where you can bubble hydrogen through that hydrocarbon, and you can saturate that hydrocarbon. And it's done with nickel as a catalyst, all right? Now, this becomes really useful in the food industry. You can do it with different things, all right? So hydrogen gases just bubble through. But and I always pose this to my bio classes in terms of making fats. So if you need, say, a particular fat for a recipe, right? Or if you're in industry and you need to make pastries, say, what do you think would be cheaper for a company to get? Animal fat or plant fat? And probably you know that when you're raising plants, you don't need to pay for vets, you don't need to pay for slaughtering, you don't need all of this stuff. So it's much cheaper to work with a plant oil or a plant fat. So you have these unsaturated fats, and then magically you can then make them saturated, right? Because if you've ever done any baking, you know that baking with olive oil and baking with lard or butter is going to give you a different result, all right? But you can take this guy, bubble hydrogen through it, and then make it saturated, all right? So the theory goes, and that's what's done, all right? So this is why you see things on labels called saturated fats, okay? But the problem is, all right, is that the chemistry isn't perfect. And hopefully by this point in the course, you understand that in reality, chemistry isn't always perfect, all right? We try to make it as perfect as possible. So you end up with some leftover double bonds, all right? Now, the thing is, and I just talked to you about cis and trans, normal double bonds that we encounter in our fats are going to be cis, and we can digest those. However, if you take a vegetable fat and you hydrogenate it, you will end up with some of those double bonds being trans. And they're not so good for you because you have trouble breaking these down. You can to a certain degree, but not at the levels that we consume them when we have these processed foods. So this is why, you know, you look at your label and you look for trans fat and you want to stay away from that. But there's a trick, all right? They can say 0 grams trans fat because, and I know everything sounds like a conspiracy, in a way this is, it depends on the percent that you have. So what will happen? So they can say 0 trans fat if they say their serving size, so here 4 cookies, is small enough that the percentage is low enough that they don't need to report it. Now, how do you spot it? Well, you look for the ingredient list and you see things like hydrogenated oils and partially, this is the trick, partially hydrogenated vegetable oil. And you know there's trans fats in there despite what they want to put up here, all right? So watch out for that, all right? Now, other things, aromatic hydrocarbons. Now, as I said, those are going to have benzene in it. And I sort of already talked about that. So you've got a 6-carbon molecule. They're super, super stable, but understand that these double bonds can flip between carbons. So that's why I said that we often draw them in a ring in the middle, all right? Really interesting properties, okay? So these aromatics have very particular properties because they've got these rings in them, all right? Let me make sure I didn't miss anything, getting on with myself talking about trans fats. All right, so aromatic hydrocarbons are gonna have these rings in them. So here you've got a whole bunch, and you've probably heard of some of these things like naphthalene, toluene, other ones you might not have, ethylbenzene, but there are many of these, okay? So these are called substituted benzene rings. These are aromatic hydrocarbons. So that you can see it's not just the ring, but here you can see there's a methyl group in here. Here's an ethyl group added on here. Here you've got two of them put together. Here you've got two methyls on here, right? So if you replace the hydrogens, okay, these things are called substituents, all right? So if you replace the hydrogens with something else, called substituents. Now, let's move away from carbons and hydrogens, all right? You can substitute other things for hydrogen, all right? So if you look at your halogens, that's group 7, right? You've got a valence of 7, you've got 1 electron free, would love to make a bond, and it can easily replace, well, I wouldn't say easily, but it can replace the hydrogen. So here, if you look at ethylene, you can replace those hydrogens with chlorines, right? So now you have here, they call it, you can probably figure out what this means, tetrachloroethylene, right? So you've got your ethylene, tetra meaning 4 chlorines. So you know that all of those hydrogens have been replaced with chlorines, all right? So this is a synthetic, right? Or you could substitute with any of the other hydrogens. So bromine, fluorine, right? The most common ones are chlorofluoro. You can get here CFCs. I mentioned those already about breaking down ozone, right? So CFCs are chloro and fluoro. So they've got chlorine and fluorine, all right, attached to those carbons. So chlorofluorohydrocarbons. I listed those in my notes on page 5, right at the bottom by slide 21, 22, okay? So why are those dangerous? So I'm going to get into that, right? So when chlorine is substituted for one or more of the hydrogen atoms, they're called chlorinated, and they're really useful. All right, so I list a couple here. Dichloromethane is a solvent. Trichloromethane is chloroform. It's an anesthetic. Now it's considered hazardous. It's carcinogenic. And then CFCs, right? So why are these guys so dangerous? These are the things I had mentioned to you used to be in aerosol cans, and they started degrading the ozone layer. So remember when we talked about oxygen, when we were talking about redox, right? We said that up in the stratosphere, we have a lot of ozone. It would protect us from UV light coming from the sun, right? So up there, it's not dangerous to us in terms of our body, but it's very protectant, that it's saving us from the ozone layer. Now, the thing is, CFCs were used a lot in aerosols. Now, why were they causing a problem? Well, they would, they're aerosolized, they go into the atmosphere, and here you can see a little bit of the chemistry. So remember, ozone has an extra carbon, an extra oxygen, and it's quite reactive. That's why it's dangerous to us in terms of a living molecule, living beings, when it's down at our level. But up in the ozone layer, it would, has chemical property that would sort of block these ultraviolet rays. But what's going to happen here is that CFCs love to react with that other carbon. They sort of act like I'm not going to say it's a catalyst, but they would react with the extra carbon, leave an oxygen, and then you get a free chlorine, which then can go back and break down another ozone molecule. So this is forming a hole in the ozone layer, which was particularly problematic, all right? And that's why these molecules were removed from aerosol cans so that we would sort of stop this. And eventually, what's happening is that the ozone layer is eventually regenerating itself, which was really an important feat. In terms of, working together as a global community, which now almost seems impossible. But you can see aerosol sprays. The other place would be refrigerants. So that's why they're reduced and banned. All right. Now, the next idea are these functional groups, and you already seen or heard me talk about methyl groups and ethyl groups. So what's happening here are groups that are added to organic molecules that actually have particular properties, and they're really important. And one of the tricks, and if you want to, just for fun, Google the difference between estrogen, which is classically the female hormone, and testosterone, which is the male hormone. And you will find out that they're almost identical to each other, but clearly have very different properties. And the reason they're different is because they have different functional groups on the main structure, all right? So these functional groups have very, very particular properties. And we're starting to play with some of these in lab, all right? So what are they? So they are groups of atoms that are attached to or part of your hydrocarbon, and they give these particular properties, all right? Double and triple bonds and halogen are also examples of functional groups, all right? So here you can see some of the names of these, and we're gonna go through them all right? So an alkane obviously isn't a functional group, but they can be added to other structures, as you'll see, all right? So here you have alkane, alkene, alkyne. The first one we'll talk about is all alcohols, ether. You can see there's an oxygen between carbons, aldehydes. We call this a carbonyl group. Ketones, carboxylic acids, which we play with in lab, esters, which we play with in lab, amines and amides, all right? So let's walk through all of these, all right? So the first one are the actual alkyl groups, right? So you can have a propyl or a methyl added to something else, all right? Right now, since we're just talking about alkanes and that, it's kind of hard to see that, but you'll see that when we keep moving forward. So a propyl would be a functional group with 3 carbons. Isopropyl would be a branch 3 carbon added to it. Butyl, sec-butyl. There's different names for them, but you can see that all of these are just hydrocarbons, all right? And they would endow another molecule with very particular properties when they're added to that. Okay, so they can be derived from the alkanes themselves. Now, the first one that you probably can understand a little bit about would be alcohol. And I in my notes, I don't do this on the slides, but in the notes, there's alcohols of interest. Methanol, so that would be a methane, right, with 1 alcohol group, and the alcohol group is a hydroxyl. It's this OH, right? So it'd be, there you go, methanol, right? Methane with an OH on it. Ethanol, all right? So in my notes, you can see where you see that. That's what's in your alcohol, all right? And 1 propanol, right? This would be rubbing alcohol. So these are different types or different common ones. And glycerol we deal with in lab, right? Here you can notice in just 1 alcohol. There's hydroxyl, there's 3, right? So you can also vary the number of these hydroxyls. And glycerol, it has a more proper name that we would actually say 1, 2, 3 propanol. So that would be a propane with an alcohol on each carbon, right? Here it would be the common name, glycerol or glycerin, all right, which you might be more familiar with, okay? We don't worry about how to name things in this course, so don't stress out about it. I just want you to know this. You take organic, you'll learn the proper way of naming things. And you can see that there's some historical way of naming things as well, which doesn't really help you in terms of drawing up a structure. But there's something called the IUPAC way of naming. So basically organic chemists got together and they thought, this is crazy. And they put a standardized way of naming. So glycerol, like I tell you, is actually 1, 2, 3 tripropanol, actually. So, but you don't need to worry about that. But there is a way of naming these so that you can tell what structure it is, okay? Okay, so important thing to remember is that alcohols are actually toxic, right? So even though you find them in your alcoholic beverages, your body looks at it as a toxin and your liver tries to get rid of it for you, which is why people who consume way too much alcohol or alcoholics often die of liver disease because their livers are just damaged from trying to get rid of that toxin. Now, you can have a benzene ring with an alcohol on it or more. They are aromatics, and they're given a special name, phenols. And these were really good at using as antiseptics. They get rid of bacteria. They burn though. So they've made some modifications, and you have this one, and this is clearly not named in a way that you could possibly remember, but hexfluorosorcinol, whatever. This is the new way of looking at this. It's less damaging to the skin, but still really effective and antiseptic. Now, the next functional group are ethers, and you've probably heard of ether, right, as a thing. But ethers themselves have two alkyl groups bonded to an oxygen, right? So those alkyl groups can vary in length and features. You can see that sometimes they can be cyclic, all right? You can see they're essentially hydrogenating an ethylene oxide with water, right? And you get ethylene glycol, all right? Antifreeze, that's what that is. So we've all used ethers in our car, right? We need them for antifreeze. This is what it looks like. So here you can see an ethyl and an ethyl sitting there, right? That's diethyl ether. This is ethylene glycol here, sorry. But here you can see that there's two ethanes with an oxygen in the middle, and that's an ether, okay? And you can vary the length and the structure and the branching. And again, you'd have ethers with very different properties. So diethyl ether, right, is one that you've encountered. This is an anesthetic. Then ethylene oxide, it's another one used to sterilize medical instruments, but of course that ethylene glycol, antifreeze, all right? The next functional group is an aldehyde. Aldehydes are usually coupled with ketones. Basically what you're looking for is this thing called a carbonyl. And carbonyl is a carbon with a double bonded oxygen. That can reside in different positions in a hydrocarbon. So if it's on the end, all right, so if you see it like this with a hydrogen, if it's on the end of the hydrocarbon, it's called an aldehyde. But of course, it can also exist in the chain, in which case you'd have two carbons out here. So the reason it just says R, because the length could be different on both sides. It could be 8 carbons on this side and 2,000 carbons on this side for all purposes. But if you see this, then it would be a ketone, right? So if the carbonyl is in the middle with no hydrogen near it, it would be a ketone. If it's on the end, it's an aldehyde, and very different properties, all right, that you get from that. Now in my notes, aldehydes of interest, formaldehyde, you've probably all heard of that. When it's mixed in water, it's called formalin. But embalming, also you find it in plastics. It's a disinfectant. Benzaldehyde, oil of almond, which is an anesthetic. You'll see it in maraschino cherries, okay? Carboxylic acids, all right? So you'd be thinking, well, I've got a carbonyl group, but basically what you're dealing with is a carbonyl group on the end with the other, instead of being a hydrogen here, now you have an alcohol. These are acids. Very common with benzoic acid. So here you can see you can have benzene ring here, or you can have a hydrocarbon. But if you see this, you're dealing with an acid, all right? And again, we use this in lab, right? So when we combine your acid, and when we're making our soaps, right? So remember that you're dealing with these carboxylic acids, all right? Just to keep in mind, all right? I know we didn't get quite into that, but something to keep in mind. Now, so when you have different types of these acids, right? So things that you can interact with or you might have heard of. So a number of them would be formic acid. These are in my notes, page 9, if you're wondering where I'm getting this stuff from. There's things that you can think about. So formic acid, where do you see that? Ant venom. So if you get bit by an ant and it bothers you, that's formic acid. More commonly known, well, not commonly, but more properly known as methanoic acid. So that tells you it's basically a methane group with carboxylic acid on it. The other place you'd see formic acid is in wasp and bee stings. The other one is acetic acid. This one is actually properly called ethanoic acid, so 2 carbons with an acid on the end. Vinegar, butyric acid, properly known as butanoic acid, body odor, and benzoic acid. You're going to see that a lot. Benzoate, that's how you recognize it. It's used as a food preservative, and it's also found, curiously, in athlete's foot ointment, which I did not know. The benzoic acid, and you actually have receptors to absorb this and to taste it, but it is the preservative, and your brain thinks it tastes good for some reason, but we'll talk about that later. Esters, again, we have a whole lab on esters. These are fun, but what are they? Well, as we said in lab, you're combining an acid with an alcohol. So when we're saying an acid, we actually mean an oic acid or a carboxylic acid, and you're combining that with an alcohol, you get an ester. How do you recognize them? Well, instead of having your acid group with a hydrogen here, you have another R group. And this is how you spot them. So this double, these two O's, so one would be a double bond O, and you'd have an O with an R group. So, and, you know, again, you're not going to need to name them, but, you know, methyl, always the alkyl group that's attached from the alcohol is named first. So here's your methyl, and then butyrate. Here's your butane right here. Okay. That's how we name that. And why are they popular? Well, fragrances, they're very volatile. We can smell them, and they have very particular fragrances that we might enjoy. Not all of them are fragrances, though. That's important to understand. Those are ones that we know well, but there's also some that are used for solvents and other things. Don't quite. If you ever have a solvent and it smells bad, right, an unpleasant smell, chances are it's an ester. It's just a smell that you just don't like too much. So we have receptors for these in our nose, clearly, to be able to smell these. So I don't know if you know this, but you have special chemical receptors. So every scent that you detect, you have a particular receptor for the chemistry that that scent is derived from. So for, in this case, for these esters. Dogs have even better sense of smell, meaning they have even more chemical receptors in their nose. FYI. All right. That's why they like to smell things. But their sense of sight is not as good as ours, so they compensate that with their excellent sense of smell. All right, so little things to know. Here you've got your chart. I use this as well in lab, right? So you can see your methyls and your acids and how they combine, and then you get your interesting smells, right? So here's balsamic vinegar and things like that, mushrooms and stuff like that. Right here you can see wax. So different smells that you're very familiar with. Some are pleasant, some are not. I'm not a particular fan of anisette. Don't really like it. But mint, here you go, wintergreen. Notice this one's strong, very, very strong smell. Sort of kind of fun just to look at this. Yeah, so here wood smell. Things that you know, a lot of these are very common things. Here you go, glue. So yeah, I don't know what this means. Ethereal, really don't know what that means. But anyhow, here's your rum smell, which we did in lab, or we're doing in lab. Anyhow, different things to think about. Now, amines and amides. These are derivatives of ammonia. Again, things that don't smell good. But what does that mean? Is that, sorry, that was my phone. And it is a call that I don't know. Anyway, sorry. Hazard of doing this at home. I get constant calls from people trying to sell me stuff. The cable people wanting to sell me a new plan. Anyhow, amines and amides. Again, derivatives of ammonia. And basically, how do you recognize them? Well, they've got nitrogen in them. Remember ammonia, so nitrogen with 3 hydrogens, okay? Now what's gonna start happening with these amines is that you're gonna replace these hydrogens with R groups, all right? And you can go up to 3 different R groups. They can be all kinds of things. They could be rings, they could be aldehydes, they could be alkanes, right? And all of them are gonna be different. And then combining them with a carboxylic acid, All right, so if you have a nitrogen, you've got carboxylic acid out here, that makes an amino acid, which we're going to talk about shortly in polymers, so when we make proteins. So amino acids combine to make proteins, but we'll get back into this. So right now, amines, right? So you've got your nitrogen and you've got your R groups substituted for your hydrogens, all right? They tend to be basic. And they smell like ammonia. They give that ammonia smell, right? Depending on how volatile they are, right? If they're really big, you're not going to smell them because they're not going to be volatile. But if they're small, you will, all right? They're found in all kinds of things. So amphetamine, yes, they are amines. Cadaverine, all right, you know what that smells like. Maybe you don't, but this has that very unpleasant death smell if you've ever been around something rotting. You can see that you've got two amines on either side of 1, 2, 3, 4, 5 carbons, so propane. And there's a proper way of naming this as well. I can't think of what it is right now. But here you've got, here's an idea, 1,6-hexane diamine, right? So this is probably 1,5 methane diamine, right? So this is telling you that there's 2 amines on a 6 carbon. It's telling you where the 1 and the 6. Here you can see a benzene ring. You can see the amine is actually off of the group here. So the naming of these can be very complicated, but I just want to assure you that the new way of naming these actually tells you exactly what this molecule looks like, all right? Except when you get huge structures that are largely proprietary by different companies, they have different ways of naming these, but to a certain degree, we can name them very simply, all right? You just need to learn the pattern, all right? Now, amines, amides. So what's happening here is that you're adding in, all right? So you're adding in now a carbonyl group, all right? This is different than an amino acid, in which case the carbonyl would be out here, okay? Which we'll talk about. But an amide is that when you've got an amine directly bonded to a carbonyl group. So there you've got your amide group, all right? So this is important. You find this where? Urea, which is in urine. You also find it in fertilizers, which is why fertilizers smell funny. But that would be, so in amide, so later on when we look at an amino acid, that's important to know the difference. You'll see that when we make proteins, we'll form something that looks very much like this in between, which would be a peptide bond, all right? So, but we'll get into that later, all right? Now, heterocyclic compounds, really common. This is when you got more than one ring stuck to each other. Very common in the body. So pyrimidine and purines, these are, you find that in your DNA, in your RNA. So basically, what does that mean? Well, you've got, you know, ring structures attached to each other. So very often, instead of just having carbon in there, you'll have oxygens, nitrogens, and sulfurs, which will give really interesting properties to things. You know, just looking what I skipped over, I didn't go over some of the common amines. So you can look at that, page 11, and amides of interest. Going back over here. So now on page 12, the last page of these notes, just want to make sure I don't go too much into a tangent. And this is all I want you to know. Alkaloids. These are a very specific class of heterocyclic compounds that you can see here. They have amines in them, all right? So here you can see that. So they are very, very common. Plants, bacteria, fungi, morphine, caffeine, nicotine, cocaine, all of them are alkaloids. So you're dealing with heterocyclic compounds that contain amines. Very, very common. All right. And look at the structure of morphine. You know, really complicated. This means that this is sticking out. This is like a plane, and then this is sticking out. So very complicated structures, but definitely things that interact with the body, right? So caffeine, nicotine, cocaine, morphine, you have receptors for these, and they have very specific effects because they mimic or they're very similar to other molecules. So morphine is very similar to your endorphins, which make you feel good, right? So anyhow, and we know where all of this goes, all right? But notice cocaine and morphine, very, very different structures, all right? Anyhow, we'll talk more about that as we move forward. Hopefully we'll get to the chapter on drugs, which is supposedly our last chapter. I don't know how the semester is going to go, but hopefully we'll get there. But you'll know that they're alkaloids. So they're heterocyclic compounds with amines in them, all right? Green chemistry, and I mentioned this already, a lot of our molecules that we deal with, so a lot of our plastics, all of these are organic molecules. And to synthesize them, because they don't like to dissolve in water the longer they get, solvents are very often used. So based on petroleum or oil products, all right, also used to make these reactions take place, all right? The problem is that those solvents are non-renewable, toxic, flammable, totally not green chemistry. And I had mentioned to you that they're shifting to the idea of trying to use water. Now remember, a lot of them are not miscible, don't mix well with water. So they're developing ways so that the reactions actually take place on a little, in an island in the water. And this makes things, so I say they're floating on the surface of the water. It makes them much cheaper, safer. Water is much more renewable in terms of that. The other thing that they're trying to do is replace heating of these molecules with using other forms of energy, such as microwaves, or just agitating them. And so that's what's shown here. So they have this cavitation, meaning that you're making cavities in the water to help this with an ultrasonic probe. So they're really trying to rethink the syntheses of a lot of these organics. So it's, like I said, the chemistry involved is one a lot of people are working on because we're trying to be greener and reduce waste and a lot of these things that go into the environment because they don't belong there and they're toxic. So you can see why this would be a real huge focus of green chemists at present to try and simplify this and make the industry much better. Anyhow, I digress. We can talk a lot about that, but important to keep this in mind. All right. So I think that's the end of this chapter. So hopefully that was helpful, and we'll talk to you in the next video.